We'd like to talk about chemical formulas. All the elements on the periodic table can be written with a chemical symbol. It's not the same as the nuclear symbol. Symbols are shorthand for the elements, and they are either one or two letters long. The first letter is always capitalized, and the second letter is never capitalized. And these names are common sense. The first ones are easy, like carbon is C, nitrogen N, boron B, hydrogen H. Some which already use C, like calcium, would be Ca, first two letters. Beryllium, since boron already used B, would be Be. Helium, since H was used with hydrogen, is He. Neon, since nitrogen used N, is Ne. Sometimes they use the first and third letter, like cesium, chlorine, and magnesium. And then some of them just have plain weird symbol names, like mercury and sodium, tin, silver, gold, iron, potassium. This is because their names were derived from the Latin. When we write chemical formulas, we will use these three items: subscripts, coefficients, and empirical formulas.
Subscript
Literally means right under. So that's these numbers right here. That 3 refers to 3 oxygens. 2 refers to everything inside the parenthesis. So 2 chlorines, and then 2 times 3. Oxygen has 3, and since now you have 2 of these, you have 6 oxygens. These are all subscripts. And we use subscripts to make formulas. Here we have the coefficients. Coefficients will be used to balance the equations, and they are the numbers out front. Notice there is no number written here, but you assume that a 1 is there. 1 calcium chlorate, 1 calcium chloride, 3 oxygens. And that coefficient literally means there are 3 of these. See, 3 oxygens, but it's much easier to write it shorthand. When we write a formula, we want to write it as simply as possible, and that is called an empirical formula. For instance, water we know is H2O. You could say that it's H100O50, but we'd rather simplify it to its simplest ratio of whole numbers, and that would be H2O. When we write formulas, we're going to pay attention to 3 things again. Here we got cations, that's the positive ion. And that's going to be listed first. In this compound, Na and Cl, the positive cation, which is a metal, is listed first. The negative anion is listed second. That's a nonmetal. Same thing here with water. The H is a positive 1 cation, that's a metal, and the oxygen is a negative 2 anion, that's a nonmetal. There are some compounds that are called polyatomic ions. And what that means is there are many atoms that make up one ion, and we have a whole chart of these that we use in class. Formulas, again, are based on oxidation state. The group 1A elements, 1A all the way to 8A, indicates their valence. And the 1A elements, the 2A and the 3A are metals, so they all lose electrons, and they're going to be positive cations. And then the group mainly 5, 6, 7A elements are the nonmetals. They all gain electrons, so they're going to be the negative anions, and they would be listed second in a formula. Eventually, when we get to writing actual chemical equations, we're going to see that we have to distinguish between all the things that we're using, the formulas, the elements, and there are elements called free elements. That means they haven't bonded yet. All the elements on the periodic table are called free elements before they bond. And they exist by themselves, and they would have an oxidation number of 0. However, there are 7 right here that are, if you will, strange. We call them the Professor Hofbrinkel elements. Hofbrinkel because it spells it out, Hofbrincl. All of those are free elements, meaning they don't have an oxidation number when they haven't bonded with anything, but they exist as diatomic, 2 atoms together. The elements, when they do bond, become charged, if you will, or they have a charged oxidation number. On the periodic table that I've given everyone, you want to mark that oxygen has an oxidation number of -2, and that is almost all the time. The one exception is when oxygen bonds in a peroxide, like here, hydrogen peroxide, the stuff we put on our cuts. Oxygen, actually there is a -1, but almost all the time it's -2. Hydrogen, on the other hand, we use the oxidation of +1, use it as a metal, and again, that's the vast majority of times. There are times when hydrogen acts like a hydride, so that's like here, sodium hydride, calcium hydride, where hydrogen is actually a -1 charge. These are just common ions that you could see. Here's some metals, the alkali metals. Here are the alkaline earth metals and some transition metals. They're all positive. They all lose electrons. Here are aluminum family metals and some other transition elements that have +3 charges, cations. Then the anions, the nonmetals, group 7 are the halogens and group 6 are the chalcogens. They form the negative anions. Polyatomic ions, here's a whole chart of them. Acetate, chlorate, chlorite, cyanide, and many, many more. These are lots of atoms all together, but they act like one ion here. See, this whole column, even though there's a lot of atoms, polyatomic, they act like a -1 anion. These here, even though they have lots of atoms, polyatomic, they act as a -2 anion. Phosphate, -3 anion. And then we have a couple of them like ammonium, which acts like a +1 cation. Mercury can be a +2 cation. The polyatomic ions are used in formulas. I've given you a chart or a reference table where you just have to look them up. You don't have to memorize them, you just look them up. Notice these numbers here. Interesting. Let's go over one of these. I'm going to give you an example of writing a formula using a polyatomic ion because I'm going to talk about those for a minute. If I have hydrogen and what's called phosphate, phosphate is PO4. Make sure we understand that it is a polyatomic ion. I like to use parenthesis. PO4 has a -3 charge. It means it is many atoms. There's actually 5 atoms here. 1 phosphate, 4 oxygens, 5 atoms. But notice it acts like a -3 anion. So it's like you could just go like this and treat it like an anion. Hydrogen, if we look on our periodic tables, has an oxidation number of +1. When you make a formula, you want to do 2 things. You want to make sure the valence is complete. And that's where these oxidation numbers come in. Oxidation numbers are the charge that an atom will take on when it bonds. Hydrogen, being a metal, will lose an electron to become positively charged because it wants to fill its valence. Phosphate acts like a negative anion, so it gains 3 electrons in the process. Then the other condition for bonding is we need a neutral situation. +1 -3 is not neutral. So we would need 3 positives to balance the 3 negatives. To do that, we'd use 3 hydrogens, and that's where the subscript comes in. An easy way of looking at this is notice the 3 is here, and the 1, you don't have to write it, I could. Call this the crisscross rule, we'll get to that in a minute. But I want to pay attention to phosphate here. If you notice, phosphate has a -3 charge. What if I wanted to know the charges of the phosphorus and the oxygen? That's where I told you that oxygen almost always is -2. So now what would be the charge of phosphorus? If we look on our periodic table, it's in group 5A, meaning it normally would have a -3 charge. But here it doesn't, because you can't have 2 negatives in the same place. They would repel each other. So what we do is we make a little algebraic equation. You can see it equals -3 as an overall charge. Oxygen has a -2 charge, and there are 4 of them. So we'd write like 4 times -2. And then we add the phosphate to it. So we have phosphate plus a -8, or phosphate -8 gives you -3. Therefore, phosphate must be +5, and we'd write it up there like this.